Hey guys, welcome back. This section, we'll go into the reasons why we make use of deep learning and review some of the components of deep neural networks. Here's an overview of what we're going to cover. First video, we're going to learn the limits of classification with logistic regression. We'll look at why logistic regression requires feature engineering and how that could turn into a daunting task when we need to classify images. In the next video, we'll go over perceptrons and feed-forward networks and look at how they make it possible to create a generalized linear model. We'll proceed to add layers and observe how our model accuracy improves. Third video, we'll revisit activation functions. Fourth, we'll review optimizers, which are algorithms that are used during training to reduce our loss. Finally, we'll review cost functions, which is how we know how far away we are from the ground truth. Before we get started, let's look at a possible solution to our last assignment. On the screen is our notebook. Let's make sure we have all our installations done and our modules imported. Our data is downloaded from Kaggle. In my case, I put it on Google Drive to make it easier to access. It's in a folder called Boston. The code on the screen shows you how to connect to Google Drive and mount it as a directory. You'll need to authenticate as part of the process. Once you're done, proceed to use pandas to read the CSV. The rest of the notebook goes through the process of splitting the data frame into train and validation, defining a list to hold the names of the columns to use as features, and the name of the column that we need to predict. We then proceed to split our features into X and our target into Y. Next, we build a linear regression model. We make use of a sequential model with only one layer. The output has one neuron and no activation, implying that the activation is linear. After the model definition, we proceed to compile it. We need to specify an optimizer, as well as an error function. Afterwards, we train the model using the fit method. We pass in our features called X, our labels are Y, and the number of epochs, which is the number of times we would like to iterate over the training data while training. For this really small data set, we set the number of epochs to 500. We can see how our loss reduces during training. We can also print out our model summary and inspect it. We can run a prediction using our validation data set and compare our predicted values to the ground truth. That's one solution to the assignment. Now let's understand the limit of classification with logistic regression. Let's quickly review logistic regression, where we try to predict the class of an item based on the observed similarities with other items in that class. What logistic regression tries to do is shown on this slide, where we plot different flower measurements. What we did was plot 100 measurements of the sepal length and width. The measurements are for flowers that fall into two classes. Without any highlighting, we cannot tell which point belongs to which class. In this new image, we've colored the dots based on what class they belong to. Now it's easy to see that the measurements fall into clusters. With this new info, we can attempt to draw a line, which is called a separating hyperplane. The separating hyperplane functions as a threshold. This works well for features that are not too complex and not too many. Consider the image on the screen. If we wanted to classify the different items on that plate, we would have an interesting problem. Before we could start working with images, we have to be sure that they are all of the same size. Consider an image that is 200 pixels wide, 200 pixels tall. This is a low-resolution image, but still has 40,000 features for a grayscale image and 120,000 features if we're dealing with a color image with 3 color channels. In order to classify the objects in the image, we'll need more info than color and size. As humans, we can easily tell that the objects in the image are apples. We can also tell that the apples have different features. We cannot write simple rules to teach a machine how to tell the difference between one apple and the next. The subtleties of describing an apple are the features of the apple. Therefore, we need to ask ourselves how well logistic regression would perform on this task of image classification. We can find out by taking a look at a sample problem. We got our notebook here. Start by installing TensorFlow, then importing the needed modules. We'll be making use of the Fashion MNIST dataset. It's a dataset of 70,000 grayscale images, the size of 28 by 28 square pixels. these images fall into 10 categories. We'll use 60,000 images for training, 10,000 for validation. So we proceed to carry out the split. We can inspect our training images and we'll see that we have a 3D tensor. The first dimension is the number of images, which the remaining dimensions are the length and width of the images. The labels, which we'll try to predict, are represented by numbers. We can map out these numbers to the actual class names using a Python list. We can plot one of these images shown on the screen. Next, we'll scale the color intensity of our images to between 0 and 1 by dividing by 255. When we're done scaling the images, we can proceed to build a model. We create a sequential model, then flatten our input and pass it through a layer that outputs 10 neurons, one for each class. We use softmax activation. We compile and train the model for 10 epochs. While training, we can observe how our loss reduces and accuracy improves. When done with training, we can evaluate our model and proceed to make predictions. This will give us the probability of each class. We can use argmax to determine the class with the highest probability. Next video, we'll be going deep with layers and neurons.